Okay, so let's get started here. Since we last met, all of you should receive your assignment number 4s back last night. I don't really have any other comments, about it except for one aspect, and that is, I think most groups approach the problem number 2 involving crane a little bit differently than me. So in this particular problem, you had to use the par ll-apply function to do the actual parallel processing with the parallel package. Now, in the x argument for this function, the way that I taught you in class to create an argument value would be, let's say if you had 4 cores that you were using, the x argument would be a list that had 4 different components. And that way, par-ll-apply would send to 4 different cores, essentially 4 separate data sets. Now, that's the way I did it in my answer key. It works just fine. Please take a look at how I did it. What most of you did, though, instead was, for this x argument, instead it was a list again, but with a component for all simulated data sets. So every single simulated data set was a separate component within inside the list. Now, from what I understand of using par-ll-apply over the last couple of years, and I went back and took a look at some of my early work on it and some of the some documentation on how to use it, my understanding is that what you pass in here needed to be the same number of components as the number of cores that you specify that you're going to use, or number of threads, if you want to word it that way too. And so I was quite surprised when this worked. And so last night I spent some time, verifying that indeed it does work. And in fact, this might be even a preferred way to do it, because I think it's a little bit easier than the way that I had taught you. Because now you don't really have to worry about the number of cores you're using and changing this to reflect it. So, you're welcome to, of course, continue using that. And I'm glad you guys found that out, that it worked well. One other thing that I find a little bit easier doing it this way versus the way that I did it in the lecture notes and in the answer key is that, let's say that you have 500 simulated data sets and you have 3 cores. Well, 500 doesn't, or 3 doesn't evenly divide into 500. So you have to figure out, well, how do you deal with those remainder, let's say, data sets? Here, at least through my initial test of what I did last night, par-ll-apply handles it with no problem. And so that is obviously a very useful thing to know. Now, the way that some of you were dividing up the data sets into these 500 components, maybe it's not necessarily the most general way, or I'm not going to worry about efficiency here, but what I do want to point out is there's a nice little function that I wrote in my answer key called split.up.data. Gotta have the dots in there, which will essentially do it for you. Now, I originally wrote this, though, in the intent of using it with my way of using par-ll-apply, but you can simply adapt the split up data function to create, in this case, 500 simulated data sets by just simply taking num.core equal to 500, num.sim equal to 500, and it will work. It's a very general function that one can use. And notice how I have nice little checks in there too to make sure everything is working out well. Okay, so that's all I had to say about assignment number 4. Were there any questions about it? Okay. So let's take a look at the schedule again. So assignment number 5, we will discuss that later today once we finish the optimization notes. Then we will get into the numerical integration stuff after that. With respect to your presentations, that is they start 1 week from today. Just as a reminder, here is the ordering that we have. So Sean and Francis will be doing it 1 week from today. Again, please make sure that you get everything to me within 24 hours of the presentation so I can take a quick look through it. Also, please remember for your presentation, I would prefer that you use your own laptop. What I recommend that you do is come into this room with your laptop, maybe a day or two before, hook up everything to make sure it works. Okay? Because we don't want to be struggling, 5 minutes into class, still trying to figure out why your laptop's not working with the projection system. It's fairly easy to use this projection system. They actually just installed something fairly new here. There are some buttons over here. There's a power button to turn that on. There's a screen button to lower this. I've noticed that I had to push that screen button a few times to get it to work. And then there's a laptop button as well too. In terms of connecting your computer to this projection system, there are 2 ways. There's a VGA cable here, and there is an HDMI cable here that they just installed over spring break. So please make sure though that everything works out. If you have problems, then that's when you need to contact me. Just don't contact me half hour before class. Say, hey, I couldn't get it to work. Well, it's a little late to be saying that. Also, please make sure that you download the Camtasia Relay recording software to your computer to make sure that it does work on your computer. So it should record the screen, and it should also record your sound. If that doesn't work, you need to come talk to me. Again, don't wait until like a half hour before class to get that done. It's very important that we can record these presentations, not just like for the same reasons that I record mine here so that people can review them, but also for me to grade. And so if we don't get a working recording of your presentation, I will take off points because it's that important. I typically rewatch these presentations at least once, sometimes twice, when I do my grading. In terms of a style for a presentation, remember I've given you 2 examples on my website. I guess my preferred way, but I'm not going to hold you to do this, is can't think of his name, not Amy. Trevor, in terms of how he had bullets for his main points, and he had short sentences corresponding to that. Note that that's a little bit of a different style than what I do with my lecture notes. It's just because it's a little bit of a different purpose, my lecture notes versus a presentation. Now, alternatively, you can use something a little bit like my lecture notes, but just be careful with, don't have like your whole screen here being filled up with a whole paragraph, because it's hard for them, the people who are in the audience, maybe perhaps to comprehend what's going on. Also, don't just stand up here and read your paragraph word for word. I think we were seeing a little bit yesterday in the seminar at times. Not you, Robert. Don't do that. That's a very poor presentation. Very poor way to do a presentation. You should come in here prepared, have it practice, that you could give it without, you know, looking too much necessarily at your screen. Okay? Yes.
Was Amy's presentation style, like with her
It was-
PowerPoint thing, okay?
It is. I mean, it's a little bit closer to mine.
Okay.
My
So
lecture
So you
notes.
said, so Amy's would be.
But notice that she didn't have extremely long paragraphs of text. I mean, she might have more than, you know, like main points that might have more than one sentence to it. But that would be fine. And one reason why I want to bring this up is that, you know, sometimes students don't know, you know, the best way to give presentations. You know, if there wasn't necessarily a teaching component with this presentation that you're giving here, I would say you need to do it like Trevor's. Short bullets. That's the way to do it. You don't put whole paragraphs up on a slide. And you know, you can take a look at, if you want other examples, excuse me, of what I mean by just presentations in general, like what you would do maybe at JSM. You can go to chrisboyer.com and let's see now, supplementary information, and you can see some of the presentations that I've given that I've actually even recorded. For example, this little fun presentation that I did not too long ago. You can see that I have bullets, and I don't necessarily have complete sentences there. That's how you do presentations in a research format. So yeah, so you can see that if you're interested. Okay, I think that's all I wanted to say about presentations for now. Were there any questions? Excuse me. Okay. Are there any other questions before we get going? Let's see then. Close some stuff out. We left off last time on page 25. I'm going to go back and review a little bit here. So we were talking about optimization, and in particular, we are looking to maximize the log likelihood function associated with the gamma distribution, so we can find the maximum likelihood estimates for alpha and beta. And if you remember, what we did was we simulated 30 observations from a gamma. We wrote a function that calculated the log likelihood function, where the very last component was the log likelihood function, taking advantage of how the d gamma function works in terms of the log argument in it. And then we use Optum. And let me just erase some stuff here to make it a little bit easier to see. So we put the results from Optum into gam.mle1. The first argument always has to be corresponding to what the initial parameter estimates would be for using Optum. And these parameters, if you have more than one, they have to be in a vector. And the first argument for the function that you're trying to maximize has to correspond to these parameters, essentially. So that's why I have in my log L1 function, I have theta there. My function, my R function I'm trying to maximize is log L1. I can pass in my data. The method that I do this use is a quasi-Newton-Raphson method. I can use some control arguments here given in a list. In particular, we're using the -1 argument that basically allows us to minimize the negative of the log likelihood function, which is equivalent to maximizing the let's say the positive log likelihood function. I didn't mention this last time, but there are other arguments that you could put in there, such as allowing for a larger number of iterations. Take a look at the help for that if you're interested. And then lastly, Hessian equal true gives you then the matrix of second derivatives for, in this case, the log likelihood function. The cool thing about Optum is that notice we don't ever have to specify any derivatives ourselves. All the derivatives are done numerically. That's why I really, really like it. And so then what's returned to us then is a list where the par argument gives us then, in this case, the maximum likelihood estimates. Okay, let's see. So that takes us into page 25 after that short review. Now, especially in situations like this where we only have two maximum likelihood estimates that we need, this is a good opportunity to do some kind of plot to help you verify that indeed the global maximum truly was found with these MLEs. And you know, how can we do this? Well, what we can do is basically almost looks like the grid search that we started off talking about at the very beginning of the optimization section. And I'm not going to go through all the details here. I'll leave the details up to you. You will need to do it for the next assignment. And what I do is I come up with a bunch of possible values of alpha, a bunch of possible values of beta, and I evaluate the log likelihood function for each one. Once I do that in my for loop there, I then can graph all these log likelihood function values, and I can do a contour plot, or I can do a 3D log likelihood function plot. The key thing that you need to realize that when you do when you do these plots, the functions that we're going to use require you to organize the log likelihood function values in a matrix. And it might be, if you've never used these functions before, it might be kind of an odd way to think about this. And let me just draw this out a little bit. So I basically create a whole bunch of alpha values, 0.25 to 10 by 0.1. I do the same thing for the beta values. It just shows the same range because it just worked well in this particular situation. And so what I have here is kind of a table, you could say. And each component of the table contains what the log likelihood function would be corresponding to that alpha and that particular beta. And what R wants with its contour function and also its 3D plotting set of functions is it wants you to arrange all your log likelihood function values in a matrix in this format here. And so I'll take a look at my code and how I do the arrangement. It's not too difficult, but you know, if you've never done it before, it might not necessarily be totally clear how to do it. Take a look at my code of how I did it. I do some other verifications in my code to show you that indeed I did get it right. Next, to do the contour plot, I'm going to say pty equal s as a graphics parameter. The reason being is because I chose my alpha values and my beta values so that they're the same number over the same range. So it makes sense to do what pty says is to plot a square plot, or make a square plot. Inside my contour function, I can specify my values of alpha, which are all in a vector, 0.25 to 10 by 0.1. All my beta values, and then this is where you specify as the z-axis, you could kind of say, all your log likelihood function values. Then what contours do you want to show? Well, that's what the levels function, levels argument allows you to do. So I'm going to plot log likelihood function values at negative 85, negative 86, and so on. Now, I typically would run this function first without the levels argument to see what it gives me, and then I would refine it by specifying the levels with a particular contours that give me the best drawing possible. Try without the levels function, you'll see what I mean. Then I have other very common arguments. And then lastly, I'm going to draw some horizontal and vertical lines corresponding to where I know the maximum likelihood estimates are. And also, if I look at this entire matrix of, or in this case, originally my vector of all my log likelihood function values, find the maximum, I know that the maximum is negative 84.81. In fact, some of the other stuff that we've done before already gave us that. And let me make this a little bit smaller here so it all fits in. So here's my contour plot. And so we can see that, approximately the log likelihood function is equal to negative 100 right here for alpha of about 6.7 and a beta of about 1.8. It's also about 100 right here at alpha of 6.7 and a beta of about 1. So that's how you understand these contours if you weren't for sure. And so we can see that basically that my log likelihood values are continuing to increase. And the very last contour that I draw with the levels argument is at negative 85. The reason being is because negative 84.8 is, again, the maximum possible value of that log likelihood function. And we can see by where the blue lines intersect, remember those are drawn at alpha hat and beta hat, that indeed it looks like that my optimization procedure worked, that I did in fact come up with the maximum likelihood estimates. So again, the whole purpose is just to verify that it indeed does work. And I would expect that always with a gamma distribution, but you can imagine in your own research settings where you're doing something kind of new and you're not for sure, would it work or not? And if you only have 2 parameters, hey, this allows you to check that. Well, maybe in your own research you'll have more than 2 parameters. Well, that's okay, but you could probably simplify it to a particular case where you only have 2, and this allows you to do a check, which of course you should always do for any good research setting. Now, with respect to a 3D plot, let's actually take a look at it here. Do this all again. We had this all up last night, and then R crashed surprisingly. It doesn't happen very often this morning, so I didn't get it all open again. So here's a 3D plot of the log likelihood function surface. I use a package called RGL, and a number of different functions in that package. Please take a look at my code to do this plot here. And so we can see values of alpha, we can see values of beta. The z-axis again is my log likelihood function itself, and the dot corresponds to the maximum likelihood estimate. And I draw what's called a needle down to the bottom of the axis there to have it correspond to particular values of alpha and particular values of beta that are the actual maximum likelihood estimates. So, although I think it's a little bit harder to see here than with the contour plot, I think it's reasonable, if we take a look around here, that indeed it looks like that we did reach the maximum value of that log likelihood function there. If you've never used this, this way of doing 3D plots before in R, the way that I'm able to rotate the plot here is to hold down my left mouse key and then just move my mouse. And if I wanted to zoom in or zoom out, I can hold my right mouse key down and go ooh, ooh. You wouldn't actually do that. What I'm actually doing is actually moving my mouse up and down as I'm holding the right button down. Anyway. See, you can have fun with statistics. Okay, so that takes us to page 30. Are there any questions? Okay, so now remember the parameters with the gamma distribution, alpha and beta, have to be greater than 0. Note that I did not specify anywhere that they were greater than 0. And given the actual the size of this alpha and beta, at least the maximum likelihood estimates, optimum is going to work out fine. But what happens if you have a situation where maybe alpha and beta are kind of small? Well, optimum could give you something outside your range that you need for your parameters. Or it might run into situations where maybe you might have to find, you can think of other probability distributions where you need to find, let's say, the log of a negative number. Well, in terms of a, let's say if your parameter is iterating through this Newton-Raphson method like procedure, and it can become, and maybe your alpha hat becomes negative in one iteration, and maybe in your likelihood function you have to take a log of that. Well, then that's going to cause a problem. So, what's a better way to do this kind of coding is to specify that indeed you do have particular kinds of constraints to your parameters. And there is a little extra, well, I shouldn't say extra, but there's another method based upon this quasi-Newton-Raphson method that we had just used that allows you to specify those kinds of constraints. These are often referred to as linear box constraints. That's why you see the extra L and the extra B in that name. And why would you call it that? Well, if I come back to my contour plot here, we can see that my possible values of my parameters kind of fit into a box. I know that alpha and beta could be, there's not an upper bound on them, but imagine if there was an upper bound on them, they would kind of fit into a box. And so that's why that name comes about. And so to actually then do this, then we could rerun our optimum function, and we just make some small changes to it. We specify the different method, and then we specify an argument called lower, which says, okay, my parameters cannot go below 0. And we also specify an upper bound as well. Notice how I say infinity, capital I and F. If you had negative infinity, you just put a negative sign out in front of that. So then I can use optimum, and I get my parameter estimates essentially to be the same as before. Okay? So that will be one way that you can handle these constraints that you have on your parameters. Now, before I knew this was available, I would use a different method. And I think it's still useful to talk about it now because it also involves the multivariate delta method in it. And this is actually what I was taught to do when I was in grad school. And that is, especially in situations where you have maybe a 0 to infinity constraint, you could, instead of trying to find the maximum likelihood estimates of alpha and beta, find the maximum likelihood estimates of log of alpha and log of beta. So reparameterize your distribution. Why would you want to do that? Well, what's the limits on log of alpha? Well, if alpha was 0 to infinity, log of alpha would be negative infinity to positive infinity, which is what optimum is always assuming unless you give some kind of constraints. And so, well, how would you do that? I'm sorry, let me back up a second. Sorry, I'm getting ahead of myself. So, once you find the maximum likelihood estimates of these with this reparameterization, let's call it alpha tilde and beta tilde, where alpha tilde is log of alpha, beta tilde is log of beta. Once you find those corresponding parameter estimates, well then, of course you want what the maximum likelihood estimates would be for alpha and beta, so you just use the exponential function with them, okay? But then, and that's not too difficult, but what about the covariance matrix? And that's often, obviously, very much of interest for statisticians. Optimum is going to give you the covariance matrix for alpha tilde and beta tilde, but you want it for essentially, well, will be alpha hat and beta hat. So how can you find that? Well, that's where the multivariate delta method comes in. All PhD students in statistics should know about this, so let's do a little bit of intro. I don't think I've talked about it in this class, is that correct? I have not, right?
Correct.
Okay. I just was seeing a whole bunch, some people going, no, and some people going like that, answering a different version of my question, but meaning the same thing. Okay, so we can go back to Cassell and Berger to talk about the delta method itself, just to review. So if I have some random variable, this could be a statistic. If it's a statistic, of course, it's probably going to be dependent upon the sample size itself. So that's why I have an n there. This is just the common notation that people use when you're talking about various asymptotic arguments. And so the square root of n y n minus theta, let's say that that converges in distribution to a random variable w with a that's distributed normally with a mean of 0 and a variance of sigma squared. Maybe this comes about through a central limit theorem. So the sigma squared is typically the variance of y. Then, if I take some nice little transformation of y sub n, let's call it g, square root of n of g of yn minus g of theta converges in distribution to a random variable w that's multiplied by the first derivative of g of theta. Still get a normal distribution, just applying stuff that you learned in Stat 882. This normal distribution now has a mean of 0 again, and a variance of g dot of theta squared times sigma squared. Okay, so that's the regular delta method. Let's talk about the multivariate delta method. Just puts this in a multivariate sense. So let's say that y sub n is maybe p by 1. Theta is a p by 1 vector of parameters that might be of interest. Let's say somehow you're able to show that that converges in distribution to a random variable w that distributed multivariate normal with mean vector 0. So this would be p by 1 and a covariance matrix p by p. Okay. Then let's say I do some kind of transformation of y and theta. Suppose this transformation leaves you with a vector that's q by 1. Q of theta would be q by 1. And it converges in distribution now to g dot of theta. What dimension do you think that will be?
Q by 1.
Nope.
Q by 1.
No. Q by q. Because g of y, or g of theta itself is q by 1. And so when you do the derivatives, then it becomes a matrix. That's q by q. So one way to think of that matrix then is, let me just go over here. There we go. So let's say we have g of theta 1. Oh, do I want to write it like that? So this is q by 1. And then if I do g dot of theta, that's equal to essentially partial with respect to g of theta 1, partial with respect to g of partial of g with respect to theta 2. And do I got that right? Maybe it's actually q by p, excuse me. Excuse me?
This was the first derivative for the sigma.
I don't understand what you're saying. I'm sorry.
This is the first derivative for the sigma.
Yeah.
So we have to just derive once. So.
No. G of theta is q by 1 already.
Oh.
And so maybe it'd be best to put it like this.
I think g of theta 1 is, if you put the first row as g of theta 1. Yeah.
Yeah. So we'll put a 1 there. And you do the same thing down here, but now you're at q. and so on. Okay? Is everyone comfortable with that now? So let me fix this. Which makes sense because W would have to be P by 1. Yeah. So anyway, so then this is your covariance matrix then. So it's just kind of the equivalent of doing that squaring that we did when we were just in the univariate case. And so that I get a covariance matrix that's Q by Q. Okay. So now I need to, yes?
A quick question. So Yn was P by 1.
Yn was P by 1, yes.
So when we transformed it using the function, that would still be P by 1.
Well, when we transform Y, we're transforming it in a way so that we get a Q by 1 vector. Okay, so here's my new log-likelihood function that I have to write in R. What I'm going to pass in for theta is alpha tilde and beta tilde. So the log of alpha, log of beta. So because of that, one of the first things I'm going to do is actually find what alpha and beta would be using the exp function. Then my code is exactly the same as we had before with the d gamma. So while I am essentially reparameterizing, the reparameterization effect just shows up a little bit in my code, and that's it. So when I use the optim function then, rather than passing in the moms for alpha and beta, I'm going to pass in the moms for essentially log of alpha and log of beta by putting a log out there. And so then when I get back in return then, is you can say alpha tilde hat, the maximum likelihood estimate of log of alpha, and beta tilde hat. Okay? My Hessian matrix then is based upon this log of alpha and log of beta. So if I take the negative of the Hessian matrix and invert it, what I'm getting is actually the variance covariance matrix for alpha tilde hat and beta tilde hat. So for example, this would be the asymptotic variance, estimate asymptotic variance of log of beta hat. I need to transform it so it's just for alpha hat and beta hat. This is then where that multivariate delta method comes in. Because then all I need to do is form a matrix that is for, you could call it G dot. So now my matrix then ends up being e to the alpha tilde 0, 0, e to the beta tilde. Using this transformation back to the alpha and beta scale. And so I put that into G dot, do the math, and guess what? My estimated covariance matrix is essentially the same as before. So that can be a helpful little trick, if you want to call it a trick, to do this kind of stuff.
So G dot is essentially giving us the first derivative of the matrix of the first derivative.
It's giving us the matrix of the derivatives, yes. Okay, so some comments. This is on page 34. Always try to use functions available in R for distributions rather than programming them yourself, especially if it's in the, let's say, the base implementation of R. Because typically, those functions will be more efficient at calculating the quantities that you need than if you were to code it in by hand yourself. Okay? Trust me on this. It is more efficient to use what's given to you. Also, another reason is because by you programming it yourself, there's a chance of error. And so that's why it's good to avoid doing it if possible. Now, there are other optimization functions out there. In particular, there's one called construct optum that allows you to do constraints, just like what we saw with the gamma example too. And you know, you can use that one. I don't really have experience with using that one. I've always been just fine with what optum gives me itself. But you know, and unfortunately I don't have a good example of this. You can imagine more complicated constraints where you can't just necessarily specify a lower bound and an upper bound that's like 0 to infinity. You know, maybe one bound might be dependent upon the other bound, for example. Also, hopefully you can, I think one of the big things to get out of this, and you know, if we had more time, I was actually going to give you an assignment about this. One of the big things that I hope you get out of this is that, you know, while we're looking at simple settings such as a Bernoulli setting and a gamma setting, imagine now a particular setting where now you have maybe parameters that are functions of explanatory variables. So maybe you're in a generalized linear model setting, for example. You could use optum to estimate the model. In fact, you could use optum to estimate a generalized linear mixed model too. And I have an example of that at the end of my numerical integration notes. This optum function is very, very, very powerful. That, you know, lots of the models that you've been trying to estimate in your other courses can simply be programmed in using this technique. So for example, let's talk about logistic regression. Let's see here. So, for those of you who have my categorical data analysis book, this basically comes from about page 71 of the book. If you don't, that's okay. Where you would want to take a look at is line 67 of a particular program that I want to show you. So if you go to my website and you page down a little bit, you'll see my categorical book there. If you go to the Programs and Data link, go to Chapter 2, you're going to find one called placekick.r. That's going to contain the code that we're going to talk about right now. Okay. Let's see here. So all of you should know what logistic regression is. You know, you talk about it, for example, in Stat 971 at least. And you know, basically, let's assume that our y is a Bernoulli pi. So the probability of success parameter is pi. And I'm also going to put a little I subscript on the y and the pi, because my pi is going to vary as a function of explanatory variables. Specifically, let's say that it varies this way: e to the beta 0 plus beta 1 times x of I over 1 plus e to the beta 0 plus beta 1 times x of I. The standard logistic regression model with only one explanatory variable. Then my likelihood function, let's call it L. It's just going to be simply the product of I equal 1 to my sample size, let's call it n, of pi sub I, y sub I, 1 minus pi sub I, minus y sub I. So essentially what we've had before, but now we have to worry about the I subscripts more than what we did before. And my log likelihood function then is the sum I equal 1 to n of y sub I log of pi sub I plus 1 minus y sub I times the log of 1 minus pi sub I. Excuse me?
N minus y sub I.
What?
On the lower it should be n minus y sub I.
No. Here, this will help you. You really wanted the brackets. Okay, so what this pi sub I, so we've seen this log likelihood function before, and we actually programmed it in before, except for we didn't really pay attention to the yi part, the pi I part. And so if you wanted to, you could substitute that logistic regression model into here. Now, note that we have two parameters, two regression parameters, beta 0 and beta 1, and we like to find maximum likelihood estimates of them. So let's take a look at how I would actually program this in R. This is again line 67 of placekick.r. So here's my log likelihood function. I have a vector beta that's going to contain beta 0 and beta 1. I'm going to pass in my covariates. For those who have me for categorical, this actually corresponds to, again, the place-kicking data set where you're using distance as an explanatory variable. And then y is going to be my 0 and 1 responses. Then I find my pi. So exp, I take the first value out of my beta vector, which is my beta 0, plus the second value out of my beta vector, which is beta 1, times x. And so what this is going to do for, and I have, I think, a sample size in this particular example of about 1,400, 1,500 observations, is going to find a vector of pi's that are about, it's going to be 1,400 by 1. Okay? Then I write out my log likelihood function just like what we've seen before. The sum of y is a vector of all my 0s and 1s, log of pi plus 1 minus y times log of 1 minus pi, and I sum them all up. That's how I find my likelihood function, log likelihood function. Then to use the optimum function then with this, I need some parameter values to start at for beta 0 and beta 1. So what I did was I just fit a simple linear regression model to my data. I specify my function of interest, specify I want a Hessian matrix. Using the ... argument, I specify x, I specify y. Same controls we've done before. There's the same method as what we've done before. And then what I get out then, I already read in the data. I mean, the data here is not that important for what we're doing, so that's why I'm not going to go over the whole problem. There we go. And so what I get here is here's beta hat 0, here's beta hat 1. Compare that to what you will get, let's say, with the GLM function that fits generalized linear models in R, and they will all match up. And you can go further, play around with this with the Hessian matrix and find the estimated covariance matrix as well. Unfortunately, I'm just kind of going randomly through screens here. So there's that Hessian matrix. So I'll take the negative of the inverse of it. And it's going to match up with what the GLM function gives you. Well, would someone ever want to do this in practice? Well, no. We got the GLM function. Why am I telling you this? Is because, well, when on your own research, when you might be developing, let's say, your own kind of model out there, maybe, depending upon what your research is, all you have to be able to do is program in a log likelihood function or whatever kind of function maybe you're trying to maximize, use Optum with it, and you have a very simple way to estimate the models. I like to always include this. Well, the reason why I included this in my book, and I actually used to actually include it in a lecture when I taught Stat 875. I took it out due to time restrictions. I think I took it out. Did I take it out? Yes. Okay. I took it out because again, due to time restrictions. But what this allows you to do is it forces you to understand fully what logistic regression is. Can you actually program that likelihood function? Can you actually optimize it yourself? And so it's a very useful learning tool, and that's why on page 71 in my book, I actually include a whole example on it. Are there any questions about that? Okay. So there's other, as I was kind of saying before, there are other potentially useful functions to use with optimization. We've already talked about uniroot. I'll let you take a look at some of the other ones on your own if you're interested. Most of my research I've been able to just simply use Optum, and I have used it a considerable amount. Okay, so that concludes the optimization section. Are there any questions? Yes.
I'm just curious. You know how when we specify and multiply by -1 so that we maximize it, is there ever a time when we would want to not do that, or is there certain fields that don't want to minimize something?
Well, whenever we're doing maximum likelihood estimation, you would always do it.
Right.
Now, if you're trying to, let's say, minimize some other function, maybe for some reason you want to minimize the expected value of something, okay? well, then that would be a place where you wouldn't do that negative.
But mostly we're in statistics, aren't we mostly concerned with
If you're doing maximum likelihood estimation.
Okay.
There's a number of other applications where you might want to minimize something.
Like cost, for example.
Yeah, minimize cost for something. I know, like for example, my research, I'm very interested in minimizing something. It's interesting that the way to do that -1 didn't come about, I think, until maybe about 8 years ago. Before that, you always just had to write your log likelihood function. At the very end, you put negative sum of whatever. Unfortunately, they added it, and so it's a little bit more convenient.
So these functions here, those are all optimization functions.
Yep.
So do you get the global optimum for all of those, or?
You're not necessarily guaranteed, no.
Okay.
And that's just the whole issue with optimization.
Mm-hmm.
Okay? And it would be nice to have a problem where you always would get the global, but that's not necessarily always the case.
Is there anything like that?
Excuse me? Well, I mean, if you could do a grid search, you would be guaranteed, if you do a fine enough grid search, over, let's say, all the alphas and all the betas, you'll find it. You'll find that global maximum. The problem is, do you have the time to do that grid search? And then there's other functions out there too that you have to worry about. There are cases where maybe, maybe you can only have integer values for whatever you're doing. Let's say maybe your alpha and beta can only be integers. Well, then that takes you into a different kind of realm of optimization. You could do something called integer programming to try to find the integers that maximize or minimize a particular quantity. And there are functions available for that too. Okay. So this will just give you some background or some experience with numerical differentiation, numerical optimization. And it's based upon something I ran into a few years ago, where what people often want to do is model wind speeds to try to understand them. And why? Well, obviously, the number of wind generated electricity is going up, so it's very important to understand how windy it is, let's say in certain parts of the country, so that they can say, well, should we build a wind turbine here or not? And in the most basic aspects of modeling wind speeds, they often use what's called a Rayleigh distribution for it. There's a reference if you're interested. So let's let x be a random variable denoting the average wind speed during a February day in Lincoln. So the reason you don't have to worry about the average there, and I don't know exactly how they calculate it, but there's places on the internet that you can download wind speeds for locations. And a number of years ago, I found a location that gave me essentially for every day the average wind speed. How are they doing that? Is it every hour they go outside and they look, well, what was the wind speed? Or is it every 30 minutes? Is it, what is it? But we have an average wind speed, and let's just work with it. And so this is what a Rayleigh distribution looks like. There's a variety of different parameterizations of it. This is just one of them. So you may find other ones if you do any searches out there. So notice it's just based upon one parameter. So it's a very basic distribution. And so there's a file on my website that contains the average wind speed values for Lincoln from 2000 to 2004 and each day in February's. Now you might be thinking, well, first of all, let me show you it. So for example, in 2004, the first day of February, it was 9.4. Now you might be thinking, okay, there should be some kind of autocorrelation that's going on here. You might be thinking, well, if the first had a windy day, maybe the second should have a windy day, or so on. And yeah, that is a possibility that we we do not have a random sample, but we have actually dependence in our sample. One thing that I did do was I looked at, well, what were the autocorrelations? And basically what I was finding is that the autocorrelations were kind of small. And so, okay, well, it's not perfect. We can assume independence for the purpose of this assignment. So part A here takes you back to your set 883 days, and I want you to derive, without using the computer, the maximum likelihood estimate of beta, the method and moment estimator for beta, and give you a big hint there to help you out for the method and moment estimator. And then also then using the asymptotic normality and maximum likelihood estimators, find the estimated asymptotic variance of the MLE. So what are you going to be looking at there? What would you need to do that? The second derivative of the log likelihood function, right? Okay. Then part B, now using the data, tell me what the maximum likelihood estimate is, tell me what the moment estimate is, tell me what the estimated variance is. Okay, so you can do all this stuff by hand, but similar to what I was talking about in previously in my notes, it's nice now that we have a way to compare what the numerical differentiation, numerical optimization procedures are going to give us. We have a way to check what the answer would be. So then in part D is that let's use the f-deriv function to find some derivatives. So let's find the first derivative of the log likelihood function, and let's evaluate it at 7, the maximum likelihood estimate, and also 8. So when you evaluate the maximum likelihood estimate, what should you get? So you're evaluating the log likelihood function, the derivative of the log likelihood function at the maximum likelihood estimate. What should you get?
The score function.
Well, yeah, it's a score function until you're actually, let's say, evaluating it at a particular value. 0. Right? Okay. So then you'll know if you did it right.
Quick question about part B. So we do not need to use any function, that just find it numerically.
Just find it numeric. Just plug in the x's. So you might see maybe the product of the x's or the sum of the x's in there and find the maximum likelihood estimate. The second part here then says, well, find the second derivative using f-deriv and use that to find what then the estimated asymptotic variance would be. Then part E says, okay, why don't you use the optim function now to find the maximum likelihood estimates and also the maximum likelihood estimate for beta and also the corresponding variance. So you would say Hessian equal true and you get it out. Okay. Now, part 2, or number 2, says, well, let's generalize this a little bit. The Rayleigh is actually a special case of a Weibull distribution. Again, there's a number of different parameterizations out there for the Weibull distribution, so you can write it different ways. Here's the one that we're going to work with right here. And you can see the relationship between the Rayleigh and the Weibull distribution. What I want you to do first is actually show me some of your derivations, find the method and moment estimates for gamma and lambda, the 2 parameters of the Weibull. Note that you'll get to a point where you will have to actually use, you'll get 2 equations and 2 unknowns, and you're not going to be able to come up with a closed form solution. So I use the uniroot function to help me. To find what the actual moms were. Then, in part B, find the maximum likelihood estimates using optim. Use the moms for your starting values. And then part C, let's do some contour and 3D plots, just like what you saw with the gamma example. And lastly, part 3, construct some histograms and EDFs, plots, of the data to examine whether our Rayleigh or Weibull distribution work well for the data set. So you put the MLEs for the Rayleigh in there, or the MLE for the Rayleigh, put the MLEs for the Weibull distribution, do these kinds of plots, and tell me, well, which fits better. Do we need to have this second additional parameter of the Weibull, or does the Rayleigh do a sufficient job? So that's assignment number 5. I don't think it's going to be too difficult. Are there any questions? Okay. So So next we have numerical integration. Obviously we're running out of time here, so I'm just going to briefly mention something regarding it. So, you know, obviously numerical integration has become a lot more needed for statisticians to understand, especially since I started grad school. And the reason is, I'll give you two reasons. One, Bayesian stuff has become a lot more prevalent, because whenever you're doing some Bayesian analysis, you're typically taking some kind of integral. There's a variety of different ways to do those integrals. We're going to focus on one way here. And then second, you know, like a generalized linear mixed model. You know, it wasn't until over 10 years ago did we have a simple way to estimate these kinds of models with like a proc in SAS or a function in R. And part of the reason is because of the numerical integration part. Could be difficult. And so now we have techniques to do this. And so we're going to talk about one particular technique here. One way that we've kind of already talked about doing numerical integration is using Monte Carlo simulation. We'll go back to that section, you'll see that. Okay, I don't think I'm going to be able to talk anymore. So we are done.